So good evening, everyone. My name is Miriam. I'm from Yahoo Labs. So first of all, thanks, Lenny, for inviting me here. So in the context of applied AI, probably computer vision is one of the main topics. And in computer vision, what we do is that we teach machines to see and understand images and videos and recognize objects and scenes and so on. And today I will show you a particular aspect of what machine vision is, because I'm going to show you some research work we have been doing at Yahoo Labs to estimate through computer vision subjective image properties. So machine vision, as we know it, have reached impressive results in the detection of visible, tangible objects in images and videos, such as, for example, faces, cats, dogs, and so on. However, when you look at an image, you don't only see what is visible. You don't only see objects, because there is a whole world of invisible properties, intangible, subjective attributes that we attach to an image when we look at it, but we can't really see them. So, for example, I can say, oh, this image makes me happy, but there's not an object called sentiment as there is an object called face. Or I can say, this image is beautiful, but I can't really see aesthetics as an object. And so, in the recent years, machine vision researchers, including myself, have been trying to model these properties of images and videos using a computational approach. And to do so, computer vision knowledge, as we know, it should open up and bridge with branches of human knowledge that sometimes have absolutely nothing to do with computer vision. This is, for example, sociology, anthropology, psychology, and so on. And so today, I'm going to show you how at Yahoo Labs we borrow techniques and theories and we bridge computer vision with these other disciplines to build effective machine vision systems. So one of the branches of subjective machine vision that have been widely explored by myself and my colleagues is called computational aesthetics. And what we do in computational aesthetics is that we build computer vision systems that can automatically assess the beauty, the photographic quality of images and videos. And we do so by teaching a machine how to distinguish between good and bad photographs according to some encoded photographic rules. And what we do at Yahoo Labs is that we tackle the problem of computational aesthetic under a specific perspective. That is, we focus on the more narrow image domain of portraits, so images with faces only. So ideally, we want to build systems that, given a portrait, estimate the beauty of this image with a face. We really don't care whether the person depicted is beautiful or not. We want to know, through a machine, whether the image, the composition of the image is beautiful, knowing that there is a person in it. And so you might ask why, if you already have a computational aesthetic framework out there, would you need a specific computational framework for faces, for portraits? Well, as computer vision researchers like to say, an image is worth 1,000 words. But if an image is worth 1,000 words, then a face image is worth an entire story. Because faces and portraits typically depict humans, and humans come with all their problems of being human. So their lifestyle, their sentiments, their history, and so on. And so actually photographers, when they take pictures of people, they have to follow specific portrait photography rules to convey the humanity of the subject they depict. And so if portrait photography is a separate branch of photography, we thought that computational portrait aesthetic should be a separate branch of computational aesthetic. And so with this observation, we built this computational portrait aesthetic framework, and we do so by taking a large data set of images annotated by professional photographers, and then reduce it to a portrait data set only by running a deep learning-based face detector on it. And then we take the output of this deep learning face detector, and we build on top of the output by designing some visual features inspired by portrait photography. This means that we go into portrait photography literature and we map each of the rules that photographers follow to take pictures of people into a computational approach, into a visual feature. And then we feed a machine learning framework with the features computed and the photographer's annotations. And we teach, by doing so, the framework to distinguish between good and bad portraits. So this is a plot of the results. It doesn't tell much apart that this system works very well in terms of scoring portraits in terms of their beauty. And it works better than general computational aesthetic frameworks. And this justifies the fact that we actually build a specific framework for estimating the beauty of images with faces. And also, the previous speaker talked about interpretability. The nice thing about this framework is that because we carefully design each feature to be interpretable, when we look at how the system behaves when assigning aesthetic scores, we can also understand what makes a portrait beautiful from an algorithmic perspective. And so there are, for example, some features that are positive indicators of portrait beauty, such as, for example, the sharpness of the landmarks or more artistic properties like the originality or the uniqueness of the image composition. There are some negative indicators of portrait beauty, such as, for example, the excessive balance in exposure or the excessive use of colors. And then there is a third group of features that actually does not correlate at all with portrait beauty. And these, when things don't work, the scientists out there know how frustrating this can be, right? When things don't correlate, there's no signal, it's very sad. But in this case, we have a nice message because this tells us that no matter the race, the gender, or the age of the person depicted, if the photographer is good in conveying the humanity of the subject, is good in his artistic work, then the resulting portrait will be beautiful. Okay, so still in the context of computational aesthetics, I'd like to show you a work that we did at Yahoo Labs with some colleagues, including Luca, who is over there, in the context of Flickr. As you might know, Flickr is a large online photo sharing platform. It has millions of users and billions of pictures. It belongs to Yahoo. And what happens in Flickr is that only a small portion of these billions of pictures is actually visible, accessible to the end users. And these pictures correspond to the most popular pictures because popular pictures are easily retrievable, they spread easily around the network, they're simply more accessible by normal users. As a result, the vast majority of Flickr pictures is actually not visible, not accessible to the final users because there are no social signals on them, so it's very difficult for them to access them. And so, with the aim of promoting good quality content to Flickr users, we thought, is actually popularity a good proxy for quality? Are all the beautiful pictures in Flickr lying on the surface of popularity? And to answer this question, we ran this crowdsourcing experiment asking humans to annotate the beauty of a large number of Flickr images. And it turned out that yes, many popular Flickr pictures are actually very beautiful. But yes, there is a large number of non-popular Flickr pictures that are actually very beautiful, according to our study. And those are what we call the hidden gems, because those are very beautiful pictures that nobody can see because there is no social signal on them. And so, with the aim, again, to promote good quality content in the Flickr platform, we employed a computational aesthetic algorithm to surface those hidden gems and provide them to the Flickr users. And so to do so, we took a large data set of absolutely non-popular Flickr pictures and ran a computational aesthetic framework on them. And by doing so, we scored them in terms of their beauty, right, automatically. And so when we rank them in terms of the predicted beauty, at the top of their ranking, we will have the most beautiful yet unpopular Flickr pictures because they come from a non-popular data set. And so those are our hidden gems, right, because there are beautiful non-popular pictures. However, because we cannot fully trust machine vision systems yet, at least, we ask again the crowd. We go back to the crowd and ask them to annotate the beauty of the surface gems, automatically surface gems. And we were very happy to see that these non-popular pictures automatically surfaced by our algorithm are as beautiful or even more beautiful than the most popular Flickr pictures. And so Oh, the data set is available, but I don't know why the link is not there. If you are interested, just write me an email, and I will give you the link. All the data is available. So those are some examples of those surface gems. Those are very beautiful pictures that have almost 0 likes, almost 0 attention in the network. And those will not be visible to normal users, to you and to me, if we didn't have a subjective machine vision system surfacing them for us. Okay, so, and because we were very happy about our results in computational aesthetics, we decided to push a bit the boundaries of what we could do with subjective machine vision and try to focus on an even more subjective dimension of visual creativity. And in particular, we analyzed creativity in the context of online microvideo. And to do so, we focus on the Vine microvideo platform. You might have heard of Vine. This is a microvideo sharing platform that was acquired by Twitter 3 years ago. And it allowed users to create and share videos with a maximum length of 6 seconds. And actually, the nice thing about Vine is that it became a very big phenomenon among the visual artist community, because visual artists realized how the 6-second constraint would actually extremely foster their creativity. And so the notion of Vine is very much related with the notion of creativity. However, what happens in Vine, as many other online photo sharing platforms, is that not all Vine videos are actually creative, and 99.19% of the videos actually look very much like this one, rather than this one. And so, with the aim of spotting the creative videos in the Vine platform, we decided to build a machine learning framework, a subjective machine vision framework, that can automatically assess the creative degree of Vine videos. And to do so, we had to face a number of problems, as you can imagine, because this was a completely crazy task. So first problem is, what is creativity? And creativity is a notion that have been defined by pretty much every branch of the human knowledge, from philosophy to mathematics to computer science. And so we had to dig a bit into the literature, and eventually we came up with this shared definition of what is creative, where something creative is something new, so it has some novel aspect and valuable, so it has some benefit for the final audience of the artifact. And so after defining creativity, we had another problem that was, how do we teach a machine to evaluate creativity? And to do so, we designed some features specifically inspired by our notion of creativity. So we designed some visual features to model microvideo value, and some visual features to model the microvideo novelty, because something creative is something new and valuable. And third problem, we know what creative is. We kind of know how to teach it to a computer, but to teach it to a computer, we need ground truth. So how do we find a data set of Vine videos annotated with creativity? So we go, again, back to the crowd. We ask a number of crowdsourcing contributors to annotate the creative degree of 4,000 Vine videos. And now with the annotations and with the features, we can feed a machine learning algorithm that will learn how to distinguish between creative and non-creative videos. Again, this data is available, but I don't know why there is no link on this slide. So please ask me if you want to see it. So we were very surprised about the results, because this system is able to detect creative degree of a video with 80% of accuracy. And also, again, because we focus on designing explainable features, when we look at how the machine behaves when assigning the scores, we can understand what makes a video creative from an algorithmic perspective. So, for example, there are some aspects like the visual novelty of the video, the presence of loop, the smoothness of the surfaces that positively correlate with the creative degree of a video. Yeah. So how am I doing with the time? I don't know.
You got 7 minutes.
Okay, so 7 minutes.
Well, you got between 7 and 17, depending on how you want to leave.
Okay. Okay. So let's do like this. So this the last chapter of this talk is dedicated to a work that we have been doing recently with a number of researchers from all around the world. And it's about estimating an even more subjective notion in visual perception, which is the notion of sentiment. What is more subjective than sentiment? Well, think about love. If I was asking you to put this emotion into pictures, probably each of us would assign different visual concept to this emotion. Because emotion perception is very subjective, and it very much depends on our cultural background, our profession, our education, whether we had a good or a bad day, and so on. And actually, together with other researchers, we have been trying in the past to study ways to automatically detect sentiment in online photo collections, for online photo sharing platforms. But the error in which we incur very often is that we tend to consider photo sharing communities as single monocultures. Well, actually, users are very fragmented, and they're different in terms of their demographics, their education, their nationality, and so on. And on top of that, what anthropology tells us and what psychologists tell us is that one of the main factors impacting our emotion perception is the cultural background where we grew up. And so we team up with this amazing multicultural team of researchers from Columbia University, IBM, from all around the world, to build a framework that would allow us and the whole community and everyone outside the community to study the impact of culture in visual emotion perception under an algorithmic perspective. And with this project, it's just started, we want to answer a huge number of questions, including, are we able to build visual sentiment detectors specific for each culture, and or how similar or different are cultures when perceiving visual emotions in online image collections. So the first step towards reaching this goal is to build a data set that allow us and other researchers to explore this dimension. And so we built this data set called Multilingual Visual Sentiment Ontology. Here you have the link, at least for this. It's a very large data set of more than 7 million Flickr pictures coming from users of 12 different languages. And each image is annotated with the language of the user that uploaded it, a positive, negative sentiment value arising from the metadata sentiment analysis, and some emotion keywords that tend to co-occur very much with the words in the metadata. To build these data sets, we had to design an ad hoc pipeline, because this is the first time that in multimedia vision community we build such a large-scale data set exploring this dimension. I'm going to skip the details, but basically this is about pulling the data from Flickr and polishing with the hell out of natural language processing, crowdsourcing, visual analysis, and so on. So it was a very big work, but the important thing is that it's there and you can use it and to help this project that we are carrying out with these guys. And in the context of this project, I'd like to show you one first simple experiment that we did to explore the impact of culture in visual emotion perception, which is about building language-specific sentiment models and then comparing them to understand how different cultures perceive similarly visual sentiment. And to do so, we take images from 6 of the main languages of our data set, and we build language-specific sentiment detectors. And then we compare them with cross-lingual sentiment prediction to understand differences and similarities between these different languages. So the idea is that for each of these languages, we take all the images and we process them through an AlexNet type of deep learning network. And through a lot of processing, we then perform sentiment classification on them. So the idea is that for each language, given an image, there is a network and there is a classifier able to output a positive, negative sentiment value for that image for each language. So we have one of these detectors for each language. And the results here, they look good in the sense that they're much better than any random classifier. We don't really know how to compare this with other baselines because this is the first course of its kind. But what we can do to understand a bit more these detectors is to perform what we call cross-lingual sentiment prediction. And this is about estimated the sentiment of the images in one language given the sentiment detectors trained on images from other languages. And so it turns out, looking at the aggregated results, that language-specific sentiment prediction works much better than cross-lingual sentiment prediction. And this makes sense because each detector is dedicated to a single language. But when we carefully look at the result, we can also understand what are the most similar language in terms of sentiment perception in this data set. So for example, we can see that the sentiment of Chinese images is the most difficult to detect from detectors trained on other languages. So the sentiment of Chinese images is very far from the other languages. And on the other hand, when we try to perform cross-lingual prediction between French, Spanish, and Italian images, then this works much better. And this makes sense, right? Because those are more Mediterranean cultures, and we tend to share the same way of understanding sentiment, right? I think I have to conclude. These findings and many others of the current research we're carrying out tell us that actually computer vision and machine vision are very powerful tools to understand how we perceive visual data. And again, I want to stress the importance, and I really like your talk because of this, of the interpretability of those features, of those systems, because this is the only way for us and for the scientists of these other disciplines to understand how humans perceive, subjectively perceive images and videos under an algorithmic perspective. And with this, I conclude, and I want to thank all these people that collaborated with me. This wouldn't be possible without them, and Yahoo Labs, and all of you, and Lenny. Thank you.
So I've got a quick question. Last time I saw you do this presentation, you had a slide about the different levels of sentiment based on nationality.
Here,
do you still have that?
You talk, I mean...
No, I think
it's here.
I found that really interesting last time. I'd love to see it again.
I think it's here somewhere. Wait. Oh, there is no? Okay. Don't hide this slide. You want to see the sentiment?
Yes, you just keep presenting in the education.
Can you see it? Yeah. So, should I command this? So, this is the average sentiment for each of the languages in our data set. The average sentiment that we detect according to the metadata. And so, as it's written there, please interpret with caution because the process through which we arrive to this plot can introduce a lot of bias in what we do. Of course, I'm very happy to see that Italian and Spanish are among the happiest population in Flickr, but we have to get a bit more into the literature, into the psychology literature, into anthropology literature, and really understand whether these findings match some of the findings that those guys have done long time ago with offline communities, right? So we have plenty of these plots if you want to see it. There is also another one about emotion, but this just tells us that there are different patterns in visual emotion perception for each language, and that there is a need for us, vision research scientists, to understand them.
Cool.
Okay?
Is there any questions from the audience?
So at the beginning, when you started talking about analyzing the beauty of pictures, you showed a picture where there was an image overlaid of the golden ratio. Yeah, is that right?
Yeah.
Like this spiral over the picture?
Golden ratio.
Does that mean you started to model somehow the beauty in a mathematical way and then test it with users? And if so, what kind of modeling did you use? before testing it with users?
So it's more or less what you're saying. So as you can imagine, to teach to a machine to distinguish between good and bad photographs, you have to give the machine tools to evaluate this aspect of an image, right? And so what computational aesthetic researchers do is that before the advent of deep learning, I have to say, what we were doing was to try to automatically infer by visual features how much a given image follow standard photographic rules, such as, for example, the golden ratio, the rule of thirds, how deep is the field, how disturbing is the contrast, how disturbing is the image compression, and so on. So you feed a machine with all this information regarding the image, and then the machine will associate the information with the beauty annotation, right? And we learn how to associate this information with the beauty annotation, so that for new images, given all this information, we'll learn to some extent to understand the beauty degree. Yeah.
The results match. So the mathematical and deep learning one match.
Okay, so deep learning approach is a bit different, right? So what deep learning does is that it takes an image, no matter what's in it, no matter where it comes from, and it analyzes with some absolutely uninterpretable layers, and then spits out a aesthetic score. So I have to say, in some cases, deep learning is much more effective than old handcraft features. However, as I said, this removes a bit the interpretability of what we do. So if we want to go back to photographers or to psychologists or to whoever to give them some feedback about how actually humans or photographers perceive the beauty of images, the creativity of videos, or the sentiment in images, this through deep learning is impossible. We are now working in making deep learning framework more interpretable by inverting them, by visualizing their output, by doing a bunch of things so that these can be applied to this kind of framework.
Cool. Sorry.
A slide deck is always friendly in showing you, a long story in just a few seconds. But just to understand, how much time did it take you to do each of these studies, and where was the weight? Was that actually on the tech side, or was that on the defining the model and really understanding the depth of the problem?
Okay, so working in this kind of projects has different aspects, right? So. Because we are not simply distinguishing between a dog and a bottle of beer as traditional machine vision, we have also to understand a bit of the non-techie literature regarding what we do. So personally, for example, the first work I showed you, I had to read portrait photography books. And because I'm a machine vision person, because I'm a computer scientist, I was seeing how to map each of those rules to a computational visual features. So it takes a time. It really depends. So for example, the Flickr project, it took a long time because we had to process a lot of images, because we had to do many crowdsourcing experiments and so on. So I cannot really tell you the time span, but it's around, I don't know, 6 months to 1 year. But it's more getting used to the multidisciplinarity of the project. So having a tech background, how do we interface with the non-tech people, and how do we acquire knowledge from them? And it's amazing because they also learn from our side, and yeah, that's it.
Yeah, I was just curious about the further downstream applications of this, as to whether you could run some of these systems in real time in a robot, or, for example, in a consumer application for photography, where you could start streaming the visual inputs to the camera, and then educate the user as to this is the moment at which you should take a photograph.
Yeah.
And extended that into autonomous vehicles, you could do something pretty interesting.
So for computational aesthetic, from what I know, some of the big companies that produce cameras like Canon already integrate a bit of this. Obviously, having a whole system that, given the scene, automatically updates the aesthetic score, this takes a bit more time, but it's we never tried. I saw some research this year at ACM Multimedia in which they were building demos to do these kind of things. The thing is, it's not anymore only about the machine, and it's more about the interaction with the human, right? So while we can build all the machine learning part, then when you have to apply to a real interactive environment, you need a lot of more user studies, and so it's not immediate, but theoretically the science to do this is ready to be used. Yeah.
Thank you, brilliant presentation. I was wondering, kind of merging the two topics tonight, is it possible, or does be any line of research to identify a frustrated user on a website?
No.
In terms of the speed of the action that it performs, in terms of, you know, what it does, identify something that you usually cannot see?
Yeah, so I work in a computational advertising team right now at Yahoo, and we are trying to understand how to exploit implicit signals, like, for example, what you were saying, or the fact that you bounce back immediately from a website, to understand which ads are very disturbing or are very offensive for the user. So it's definitely there. Of course, it's from this is more related to the interaction, and it's less related to the visuals. We can learn, for example, we have a paper this year at that learns how to detect offensive ads, exactly based on these kind of signals, right? But from a visual perspective, we can just reuse these signals. We cannot really use images to understand whether as feedback from the users, right? Yeah.
So I think we've got time for just one more question. Is there? Yeah. Okay.
I was interested in perhaps turning around a little bit the question of this interpretability versus this deep learning, and I was wondering, rather than even thinking, oh, how long is it you know, that we kind of hold on to this, being able to explain something to humans, you know. How about this? Is it possible that, whether it's interpretable or deep learning, but perhaps let's take the interpretable approach, to have computers teach us something about ourselves? Because that's really the reason you want to have interpretability. You want to be able to tell something back to humans, right? So would you be able to perhaps design some study like that, where right now what you're doing is take some guidance from photographers and just do statistics and say, just fast processing. Is it possible to find something from images that the photographers didn't tell you?
Yeah, it's maybe not related to photography rules, but what we're working on right now, and with some people from the digital humanities kind of research line, is to understand stereotypes, for example, like what makes you think that I am from my nationality, or what are the stereotypes for our cities of London or Tokyo and so on. And, or for example, we did a study with an ex-colleague at Yahoo Labs about detecting lifestyle aspects from profile pictures, like, for example, which kind of places you will go given your profile pictures. And by doing so, we spot how humans attach stereotypes to people. And then we show how actually the machines doesn't need this stereotype to predict exactly the same people as the same thing as people would do from profile pictures. So at this kind of level, we can discover new things, like what are the stereotypes that are actually real, and what are the stereotypes that are actually not real according to a machine, or for example, in the context of creativity, sometimes there is not so. Creativity is such a fuzzy notion that you cannot really identify what are the rules for creative videos in the context of micro video. And by performing the study that we did, we could spot at least some of those rules. Of course, this you might incur in generalization, so you don't want to incur in generalization because humans are very diverse and we are beautiful like that. But you can spot some general patterns, something like that. Did I answer your question? I'm not sure.
Perhaps
Maybe we
you
can.
had an example about these stereotypes that may be clearer. Like, what is it something that you learned that you didn't know before?
Look at this girl.
No,
Look how unhappy English people are.
No, that's the thing. It's aggregating statistics, and I think when you don't have this ability to look at a million images, that does tell you something. But it's more like, what is a feature that jumps out about stereotypes?
So, for example, with this other study, we noticed that people tend to associate the presence of female and I think some other or blue eyes with attractive or pickup places, while the machine was just associating some basic, some basic, not even face feature, but just compositional features to predict whether the place where this person would go was a pickup place or an attractive place, things like that. Or for example, a machine would say people that go to geek places tend to wear yellow in their pictures, and while people would say, okay, people that go to geek places tend to wear glasses and look older, things like that, right? So you can kind of spot the stereotypes at a human level versus stereotypes at a machine level, things like that.
All right, thanks very much.